Yeah. It's the all. So grow it's just like pop the and stuff. They make them very rare. I'm reading nice. But it doesn't have. So it's just about the. So it's just notice. You look at.
All right, guys, we're gonna get started. This is y'all's problem for today. I'm gonna give you guys a few minutes to write down what you want and start working it out by yourselves, and then we'll work it out together. All right, we'll start working it out together. So for this problem, we were given a diameter of 10 millimeters. So they're telling us that we're going to be working with the circle as it's a rod. We were given an axial force of 20 kilonewtons. We were also given a Young's modulus of steel, which is 200 gigapascals. On our figure, we were given lengths for our two segments. So for the length of AC, it's 400 millimeters. So L of AC is 400 millimeters. The length of CB is 800 millimeters. Oops, C. We were also given this 0.2 millimeters. That is going to be the total displacement of our rod. Because we have a wall here, so it's going to stop our wall at 0.2 millimeters. And I'm going to show you guys what our displacement would actually be if we didn't have this wall here. So delta represents our displacement of 0.2 millimeters. And we need to find the reactions on the rod. So FA and FB. So to go over why our displacement is going to be 0.2 millimeters, well, if there wasn't a wall there, I want to show you guys something. So you guys have been working with this equation. Displacement is equal to a force times the length over Young's modulus, which is E, times the area. So our total force for this rod would be 20 kilonewtons. So I'm going to convert it to 10 to the third. Our length for the whole rod would be 1200 millimeters. Converting that to meters, that's 1200 times 10 to the negative 3 meters. Our Young's modulus is 200 giga, so that's 200 times 10 to the ninth pascals. And our area, like I said, we're going to be working with the circle. So it's pi over 4 diameter, which is 10 times 10 to the negative 3 meters squared. So if we did not have this wall, the total displacement of our rod the total displacement would be 0.001527 meters. 1, 2, 3. So I'm just showing you guys that if this wall wasn't here, the total displacement of the rod would actually be 1.5 millimeters. But because we have the wall, the total displacement is going to be 0.2 millimeters instead. So I just wanted to show you guys that. You didn't actually have to write that down if you didn't want to, but I just want to show you. Does that make sense to everybody? Yeah? Okay, good. Okay. So actually starting to work out the problem. If you got like the PDF from Canvas, there's some free body diagrams. So for this first one, we see that they labeled our forces at our walls. So we'll have a force in the x direction at A and a force in the x direction at B. And then we also have our axial force of P. And remember, if we were to look inside, we will always have another force pointing in the opposite direction because of, I can never say this word, so I'm just going to write it down. That. So because of that, we will always have like a FA going in the opposite direction for balance. Okay? So we have been learning, well, actually, you guys should know this from statics. If we take the sum of the forces in the x direction, I'm going to do the right as positive. So if we're going to look at this rod right here, does anyone want to try and take a gamble at what our equation will look like? No one? That's okay. Okay. What was it? No, okay. You were kind of on the right track. So we have FA, but it's going in the opposite direction. So that would be minus FA. We have an FB. It's going in the opposite direction. So that's a minus FB. And then we also have our P, but that's going in the right direction. So that's going to be a plus 20 kilonewtons, equal to 0. So if we rearrange, minus FA minus FB is equal to negative 20 kilonewtons. I see that they have a negative in common, so I'm just going to take that negative out just to make it easier for us in the future. So this will end up being FA plus FB is equal to 20 kilonewtons. So usually when we're working out these kinds of problems, we haven't had two unknowns. So this is new to us. So we need to figure out another way to get another equation that also has FA and FB in it. Okay? Is everyone done writing? So I can go to the next page. All right. Moving on. We have another free body diagram. They did the segment of AC and CB. So I'm just going to label this section 1 and section 2. Now, because our P is going to the right, our displacement, so this is tension. Sorry, I'm getting kind of ahead of myself. This is tension, so our rod is experiencing like a force going outwards. So our displacement will be positive. But on segment CB, we have a compression force, so our displacement will be negative. So this is compression. Okay. So like I said earlier, you guys have been working with the displacement equation, which is delta, which equals a force times a length over Young's modulus times an area. I'm going to work out this bottom part so I don't have to do it twice because our shape is the same throughout both segments. But let's say we had a circle here and a rectangle here. You're going to have to do the displacement EA part twice. So you would have like a circle for your area, and then for the other one, it would be the area of a rectangle. But for this case, we're a rod all throughout, so it will be the same EA for both displacements of both segments. Okay? So like I said earlier, we're working with the circle. So that would be pi over 4 diameter squared. Our diameter was 10 millimeters, so 10 times 10 to the negative 3 meters squared. So our area will be 7.85398 times 10 to the negative 5 meters squared. Our Young's modulus times our area. So Young's modulus was 200 gigapascals. So 200 times 10 to the 9th pascals times the area that we got, 7.85398. 10 to the negative 5. $1.5707 times 10 to the 7th newtons. Remember, pascals is newtons per meter squared. So our meter squared would cancel, and we'd be left with the newtons. So now that we've got the bottom portion of our displacement equation, I'm now going to label our displacement of AC and a displacement of CB. So it's going to be delta is of AC. The force at delta AC will just be FA. Our length of AC is 400 millimeters. And we found our EA, so I'm just going to write that number here. Repeating for delta CB. Our force at delta CB will be labeled as FB. Our length of CB is 800 millimeters. Again, EA is that number. So just rewriting it again. Now, for delta CB, remember how I said it's compression? So that is going to be associated with a negative sign. So we're going to do negative here for our force at B. All right. Now we need an equation that relates delta AC and delta CB together. That will just be the total displacement. So I'm just going to write it as delta is delta AC plus delta CB. We already knew what delta was, as that was stated in our problem statement. So 0.2 millimeters. So 0.2 times 10 to the negative 3 meters. Plugging in our delta AC and our delta CB into this equation, it will be FA times 400 millimeters minus FB, 800 millimeters. Because they have a common denominator, I'm just going to write all that over 1.5707 times 10 to the 7th
newtons. Now I'm going to move our denominator to the other side. So let's see what that will be. 0.2 times 10 to the negative 3 times 1.5707 to the 7. So multiplying this number times this one, we will come out to 3141.4 newtons times a meter is equal to FA times 400 millimeters minus FB of 800 millimeters. I see that they have a common 400, so I'm going to take that out of there. So to get rid of this 400, divide it by 400 on both sides. And because it's millimeters, I'm converting to meters. So times 10 to the negative 3 meters. So that will get rid of that. Now this side will become 7,853.5 newtons. And we took out 400 out of here, so this will be FA minus 2 FB. So now we have our another equation that we can use to solve for our forces with the first equation that we got. So the first equation was 20 kilonewtons, so I'm converting that to newtons, so times 10 to the 3. And that was equal to FA plus FB. So this was our first equation. And you guys have learned, I think in like high school or like middle school, elimination or substitution. So if you wanted to do substitution, you could rearrange equation 1 to solve for like FA or FB, plug it into equation 2 to get one of your unknowns, and then plug it back into equation 1. I'm going to do elimination because I see that I have an FA here and an FA here. So if I multiply it by -1, I can get rid of one of my FAs. So I'm just going to do that. So then this will become negative 20 times 10 to the 3, negative FA, and then that will be a negative FB. So doing that math, this side will come out to negative 12146.5 newtons. Our FAs cancel, so we don't have to worry about those. We have a negative 2FB minus FB, so that will be negative 3FB. Dividing by -3 on both sides, we will get 4,048 newtons. And you can leave it like that if you want to, or we can convert it to kilonewtons. So 1, 2, 3. 4.048 kilonewtons. So that's our first force that we needed to find, and we need to find FA. So I'm just going to reuse equation 1 again So equation 1 was FA plus FB is equal to 20 times 10 to the third newtons. Plugging in our known of FB, 4,048 newtons. Subtracting 48 to the other side. That's equal to 15952 newtons. Or converting to kilonewtons, 15.952 kilonewtons. Now, if you were to plug in your forces back into your displacement equations, you would see that for the displacement of AC, you would get a positive number. And for delta CB, you would get a negative number, which we concluded because of compression. And if you were to add both of them together, you should get 0.2 millimeters, as that was our total displacement of the rod. Is there any questions? No? Okay. Well, that was all I had for today. So y'all have a good night. Thanks.
So,